Today, I would like to introduce our preceding paper, Security Risks of Knowledge Graph Reasoning. So I'm the first author and also presenter, Zhaohan. Okay, I'd like to start with introducing what's a knowledge graph. So the knowledge graph is a collection of some real-world objects as node, and also their relational facts as edges. And the common database like Wikipedia are like intensively used to build a knowledge graph. And in practice, knowledge graph is also widely used in some domains, in some security-sensitive domains. So for example, in the cybersecurity, it helps to build the cyber threat intelligence, building the threat engine. And also in the biomedical science, it collects a lot of like medication evidence, help to build the clinical decision and support. And to use knowledge graph with AI, people typically rely on the reasoning mechanism. So besides the knowledge graph, reasoning also have 3 more components. So the first one is query. Query could be in any raw format like the natural language, and the reasoning system will transfer it into a logical graph. And then the representation. So given a knowledge graph, the reasoning system will train the entity embedding using the knowledge graph structures. And also the last one is reasoning. So given the graph representation of the query and also the entity embeddings, reasoning happens in the embedding space. And what it do is it reduces complex query into an embedding representation, and then based on the query embedding, it matches the answers based on the embedding similarity to entities, and then find the answers. If we pack everything together, the reasoning will follow such a pipeline. So on the upstream, the reasoning system collects the raw knowledge from a lot of knowledge sources and then builds a knowledge graph. And then it trains the entity embeddings and also the machine learning models and pack as a black box. And then in the downstream inference time, a user feeds a query into a reasoning system, and the system takes the query to do the graph matching in the embedding space, and then return answers to the user. So given such a pipeline, we notice that the knowledge can come from a lot of sources. So it is like intensively reported that the knowledge graph with poor correlation of cold sourcing knowledge may lead to very harmful impacts. For example, Google's knowledge graph is reported to contain a lot of misinformation. And besides the poisoning vulnerability, we also want to point out that since the query is not raw, so it's constructed from other sources, so it could be, it's possible like the insecure raw sources may include misguiding evidence. So for example, when we want to construct the query to do the like cyber intelligence, we want to do the software testing first and then collect the evidence to build the threat report. But if the software is suffered by the repackaging attack, those mis-evidence may be included to the constructed report. So given those 2 vulnerabilities, we further propose our attack, ROR, which is reasoning over adversarial representation. So it studies both knowledge poisoning and also query misguiding vulnerabilities on the upstream and downstream against the reasoning system. So ROR contains 4 steps. The first one is surrogate KGR construction. And then based on the constructed KGR, we do latent space optimization to optimize embeddings. And then based on the optimized embedding, we use it as supervision to generate the input space attack. And then we release the input space attack to the input space, to the knowledge graph or to the query. And in the middle 2 steps, optimization, then approximation or OTA, we use it because the reasoning system is not differentiable. So we cannot just do optimization to find the attack. We have to split it into 2 steps. So how do we apply the OTA is a very critical problem. In the knowledge poisoning, OTA first optimize the entity embeddings. So to make the embedding best satisfy our attack objectives. And then in the input space, we go to the knowledge graph to find what's the best poisoning facts, such that by adding those facts to the knowledge graph, we can get the expected embeddings in the embedding space by the forwarding reasoning process. And the OTA in the query misguiding attack, so it first optimizes the query embeddings here, so to best satisfy the attack objectives. And then it further generates the bait evidence. So, or we can say it further use the reverse engineering to generate what's the perturbation of the query it should be, and then release those perturbations to the query side. And further, we want to propose we have proposed a collaborative strategy. It perturbs both knowledge graph and also a query to make them collaborate to each other to get the strongest attack. So with the above attack designs, let's move to the evaluation part. We have two attack objectives. So first is backdoor objective. We want to make any query with a specific pattern to lead to a target answer. And then the targeted objective. So we want the query with a specific pattern to lead to generally erroneous answer. So here, I will use the threat hunting use case to illustrate our experiments. So the threat hunting may contain querying the vulnerabilities or querying the mitigations. And let's first look at how effective it could be of our attack. So the backdoor attack, so if we don't launch an attack, we can see attack is totally not effective because our target answer is some low-ranked answer. But after we launching the attack, we can find the performance is significantly improved. So here the value is higher, the better. And for the targeted attack, so if we don't launch the attack, we find the system normally performed. But if we launch the attack, so we find the system's performance significantly degraded. And besides the general effectiveness, we are curious about what's the influential factors it could be. So here a representative experiment is we want to study how the prior knowledge influence our attack. So here we change the number of prior knowledge the attacker have, and then reevaluate the attack. And we found that actually our attack can return to be effective with a limited prior knowledge, like with only half of the knowledge graph facts. And besides the influential factors, we also want to evaluate our attack with alternative settings. So one important setting is the attack budget, because we cannot just do unlimited perturbation on the graph or on the query. So here we change the budgets that poisoning the knowledge graph or misguiding the query and see how does the collaborative attack perform. And you can see in the targeted attack, so if we enlarge the number of available budget, actually the performance gain is decreasing. And also in the backdoor attack, a surprising thing is if we increase the budget, the overall performance may even decrease. So we can conclude that it's not always beneficial to have more budgets on the attack. And besides those attack performance, we further want to propose some countermeasures here. So we propose two strategies. The first is filtering facts that could try to filter out those poisoning facts from knowledge graph. And the second thing is adversarial training. So we use the same query misguiding method to generate the adversarial queries and then retrain the system to try to improve its robustness. And we found that for the filtering fact strategy, actually there exists a trade-off between the benign performance and the defense. So even though we can observe a degradation to the attack performance by increasing the number of filtering facts, but the benign performance is also hurted. And for the adversarial training, we concluded that it cannot prevent the attack even using equivalent or more perturbation budgets. So the attack performance can guarantee to be more than 50% effectiveness. Okay, so I think that's quite everything of our work. So if you are interested to more evaluations, feel free to read our paper. So, and also feel free to drop your question to my email address. Yeah. Thank you for listening.